Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
This episode was generated using artificial intelligence. Please verify facts.
Hi there, Herman and Corn. So we hear an awful lot in networking about the different layers of the IP stack, and I never knew that it had a name. But you mentioned that in your latest episode, the OSI model for the IP stack, which is really the foundation for just about all forms of networking. Well, at least those based on the IP stack. But it's very important when you're debugging things. We frequently talk about layers and what layer of the stack that we're working at. So I'd love to learn a little bit more about it. I definitely come across it in the course in a kind of passive way, but I'd love to really understand what the different layers of the OSI model stack mean, and walk me through it from layer 1 through to the very top.
Hey everyone, welcome back to My Weird Prompts. I am Corn, and as always, I am joined by my brother and resident deep diver into all things technical,
Herman Poppleberry, at your service. It is good to be back in the studio, Corn. Or, well, our living room here in Jerusalem.
Exactly. And speaking of our living room, our housemate Daniel sent us a voice note this morning that actually made me realize how much we take for granted every time we open a browser or send a message. He was asking about the Open Systems Interconnection model, better known as the OSI model.
Oh, I love that Daniel brought this up. It is one of those foundational concepts in networking that everyone hears about if they spend 5 minutes in a server room, but it can feel incredibly abstract if you do not break it down. It is essentially the grammar of the internet. It was developed by the International Organization for Standardization back in the late 1970s to make sure different computer vendors could actually talk to each other.
I like that analogy. It is the framework that allows different computer systems to talk to each other, even if they are made by different companies or running different software. So, today we are going to do exactly what Daniel asked. We are going to walk through all 7 layers, from the physical hardware at the bottom to the apps you use at the top.
And we should probably start by acknowledging that even though it is January 7th, 2026, and networking technology has advanced light years since this model was first developed, the OSI model is still the primary way we troubleshoot and conceptualize how data moves. It is like the anatomy of a digital conversation.
Right, and as we discussed back in episode 252, when we were talking about mesh networks versus wired ones, understanding the layers helps you figure out where a problem actually lies. If your Wi-Fi is down, you do not start by checking your email settings. You start at the bottom.
Exactly. So, let us dive into layer 1. This is the physical layer.
Okay, so layer 1 is the actual physical stuff, right? The cables, the radio waves, the electricity?
Precisely. Layer 1 is responsible for the actual physical connection between the devices. It is where data is converted into signals that can travel over a medium. We are talking about bits here, zeros and ones. But at this level, those zeros and ones are not even numbers yet. They are electrical pulses, light flashes in a fiber optic cable, or radio waves traveling through the air for your Wi-Fi 7 or 5G connection.
So when a technician says there is a layer 1 issue, they are basically saying the cable is unplugged, the fiber is cut, or there is too much interference on the radio frequency.
You got it. It is the most literal layer. It defines things like the pinout on an Ethernet cable, the voltage levels, and the timing of the signals. If you think about the massive undersea cables like Google's Nuvem cable connecting South Carolina to Portugal, those are the giants of layer 1. Without this layer, nothing else matters because there is no path for the energy to travel.
It is interesting because we often think of the internet as this ethereal cloud, but it really is anchored in thousands of miles of glass and copper. But once those pulses of light or electricity reach the other end, they need to be organized. That brings us to layer 2, the data link layer.
Yes, and this is where things start to get organized. If layer 1 is the raw sound of someone shouting, layer 2 is the realization that those sounds are actually words. At this layer, we stop talking about raw bits and start talking about frames.
Frames. Okay, explain that.
Think of a frame as a little envelope. It takes those raw bits from layer 1 and packages them with a header and a trailer. The most important thing at layer 2 is physical addressing. This is where MAC addresses live. Media access control. Every network interface card in the world has a unique MAC address burned into it at the factory.
So, layer 2 is how two devices on the same local network find each other, like my laptop talking to our router here in the house?
Exactly. Switches operate at layer 2. When a switch receives a frame, it looks at the destination MAC address and says, "Oh, this belongs to the device plugged into port 4. It does not care about the internet or IP addresses yet. It is just local delivery within the same building or the same segment. It also handles error detection to make sure the bits did not get scrambled during their trip across the wire."
So if layer 2 is local delivery, like a courier carrying a letter from one office to another in the same building, layer 3 must be the postal service that gets it across the city or the world.
That is a perfect transition. Layer 3 is the network layer. This is the home of the Internet Protocol, or IP. In 2026, we are mostly talking about IP version 6, though IP version 4 is still hanging on in some corners. This is where we move from frames to packets.
Packets are the famous ones. Everyone talks about packet loss when their video call stutters.
Right. And the reason we need packets is that layer 2 is limited. You cannot have a single local network that connects every device on Earth. It would be chaos. So layer 3 provides logical addressing. Your IP address is your logical address on the global network. Routers live here at layer 3. Their job is to look at the destination IP address on a packet and decide the best path for it to take to get to its destination, even if that destination is 10,000 miles away.
This is where BGP, or Border Gateway Protocol, comes in, right? We have touched on that before when talking about how the internet actually maps itself.
Spot on. BGP is like the grand navigation system for layer 3. It is what allows a router in Jerusalem to know that a packet destined for a server in Tokyo should go through a specific path in Europe first. Layer 3 handles the routing and the fragmentation. If a packet is too big for a certain part of the network, Layer 3 breaks it down and reassembles it later.
Okay, so we have the physical wire, we have the local MAC address delivery, and we have the global IP routing. We have the data to the right house. But how do we make sure it actually arrives intact and goes to the right person inside that house?
That brings us to layer 4, the transport layer. This is where things get really sophisticated. The two big players here are TCP and UDP, Transmission Control Protocol and User Datagram Protocol.
I remember we discussed the difference between these two in episode 216 when we were talking about benchmarks. TCP is the reliable one, right?
Yes, TCP is like a registered letter that requires a signature. It sets up a connection, ensures every packet arrives in the correct order, and asks for an acknowledgement from the receiver. If a packet goes missing, TCP notices and asks the sender to send it again. This is what you want for things like web pages or emails where every single character matters.
And UDP is more like a live broadcast. You just keep sending and hope the other side catches most of it.
Exactly. UDP is for speed. It is used for voice calls, video streaming, and gaming. If a single frame of a video call is lost, you do not want the whole stream to stop while the system asks for a resend. You just want to move on to the next frame. But Layer 4 does something else crucial. It handles ports.
Ports, like port 80 for web traffic or port 43 for secure traffic.
Precisely. If the IP address is the street address of the house, the port number is the specific room where the data needs to go. Your computer might be doing 10 things at once. It is downloading a file, streaming music, and checking for updates. Layer 4 uses port numbers to make sure the music data goes to the music app and the file data goes to the browser.
So we have reached the point where the data is at the right computer and the right application. We have covered the bottom 4 layers, which are often called the lower layers or the transport-oriented layers. Now we are getting into the upper layers, which are more about the software and the user experience.
Right. And this is where the OSI model starts to diverge a bit from the TCP/IP model that we actually use in practice, but the distinctions are still really useful for understanding what is happening under the hood. Layer 5 is the session layer.
The session layer feels like the one people talk about the least. What is actually happening there?
It is all about the dialogue. Layer 5 manages the start, stop, and restart of a conversation between two devices. Think of it like a phone call. Layer 4 got the connection established, but Layer 5 is the part of the brain that says, okay, I am going to talk now, then you talk, then I will send this file. It handles things like checkpoints. If you are downloading a huge file and the connection drops, Layer 5 is what allows the download to resume from where it left off instead of starting from zero. It keeps your remote desktop session or your cloud database sync alive even if the network blips.
That makes sense. It is the coordinator of the session. It makes sure that even if the underlying connection flutters, the logical conversation stays on track.
Exactly. And once the session is managed, we move to Layer 6, the presentation layer. This is often called the syntax layer.
Presentation. So, is this how the data looks on the screen?
Not quite the visual look, but the format. It is the translator. Computers represent data in different ways. Some use different character encoding, some use different compression formats. Layer 6 is responsible for making sure that the data sent by Layer 7 on one end is readable by Layer 7 on the other end.
So, encryption and decryption happen here?
Yes. When you use TLS 1.3 to secure your data, that is a Layer 6 function. It also handles compression, like the AV1 video codec or gzip for web files. Layer 6 is what understands how to pack and unpack that data. It ensures that when you send a string of text, the receiver does not just see a bunch of gibberish because they are using a different encoding standard.
It is like the universal translator of the network. It takes the raw data and says, okay, this is a movie file, or this is an encrypted message, or this is a piece of JSON code for an API.
You got it. And that leads us finally to the top of the mountain. Layer 7, the application layer.
This is where we live. This is the part we actually interact with.
It is, but there is a common misconception here. People think Layer 7 is the actual app, like Chrome or Spotify. But technically, Layer 7 is the set of protocols that those apps use to communicate with the network. HTTP for web browsing, SMTP for email, or modern, API protocols like gRPC.
So when I type a URL into my browser, the browser is an application that uses the HTTP protocol at Layer 7 to start the whole process we just described.
Exactly. Layer 7 provides the interface. It identifies communication partners, determines resource availability, and synchronizes communication. It is the layer that understands that you are trying to fetch a specific web page or send a specific command to a database.
It is fascinating to see it all stacked up like that. From a pulse of light in a cable at Layer 1, all the way up to an HTTP request at Layer 7. It is like a Russian nesting doll. You wrap the data in a Layer 7 header, then a Layer 6 header, and so on, until it is a tiny little package ready to be fired across the world.
That process is actually called encapsulation. And when it reaches the other side, the reverse happens. It is called de-encapsulation. Each layer peels off its corresponding header, reads the instructions, and passes the remaining data up to the next layer. It is a beautiful, highly coordinated dance that happens billions of times a second.
So, Herman, I have to ask, since this model was designed so long ago, how does it hold up in 2026? Are there things that do not fit?
That is a great question. In the real world, we mostly use the TCP/IP model, which only has 4 layers. It lumps the top 3 OSI layers into one big application layer, and it combines the bottom 2 into a network access layer. But the reason we still teach the OSI model is that it is much more precise for troubleshooting.
Right, because if you say there is an application error in the TCP/IP model, that could mean anything from an encryption failure to a coding bug to a session timeout. But in OSI, you can say, this is a Layer 6 issue, and everyone knows you are talking about data formatting or encryption.
Exactly. And it helps us understand new technologies too. Think about software-defined networking or network function virtualization. We are moving more and more of the logic that used to live in hardware at Layer 2 and 3 into software. But even when it is virtualized, the logic remains the same. A virtual router still operates at layer 3.
I also think about things like the Internet of Things devices we have all over the house now. Some of them are so simple, they barely have a layer 7. They are just sending tiny pulses of data. But they still have to follow the rules of the stack to get that data to our phones.
They do. And it is even more relevant when you look at the massive scale of AI clusters today. When you have 10,000 GPUs all trying to talk to each other to train a model, the latency at layer 1 and layer 2 becomes the biggest bottleneck in the world. Engineers are obsessed with shaving nanoseconds off the physical and data link layers because at that scale, those layers determine the speed of innovation.
It is incredible. We went from talking about undersea cables to AI training clusters, and the same 7-layer map applies to both. It is a testament to how well those original architects understood the fundamental nature of communication.
It really is. And for our listeners, the next time your internet acts up, try to think through the layers. Is it layer 1? Is the cable plugged in? Is it layer 3? Can I ping a website? Is it layer 7? Is the specific app or service just down? It makes the whole world of technology feel a lot less like magic and a lot more like a well-organized system.
That is a great way to put it. It turns a frustrating mystery into a logical puzzle.
One more thing before we wrap up the technical side. There is a joke in the industry about layer 8. Have you heard that one?
Oh, I have. Layer 8 is the human layer, right?
Exactly. When everything in the 7-layer stack is working perfectly, but the system still is not doing what it should, the problem is usually the person sitting in the chair. It is a reminder that even the most perfect technical model has to interact with messy human reality.
Well, on that note, I think we've given Daniel a pretty solid walkthrough of the OSI model. It is more than just a list for a certification exam. It is the blueprint for how our modern world stays connected.
It really is. I hope this helped clear things up for everyone listening. It is a lot to take in, but once it clicks, you start seeing the layers everywhere.
Absolutely. And hey, if you are finding these deep dives helpful, we would really appreciate it if you could leave us a review on your podcast app or on Spotify. It genuinely helps other curious people find the show, and we love hearing what you think.
Yeah, it really does make a difference. Thanks for the prompt, Daniel. Keep them coming.
You can find us at myweirdprompts.com for all our past episodes and the RSS feed. This has been My Weird Prompts.
Until next time, I am Herman Poppleberry.
And I am Corn. Keep asking those weird questions. We will see you in the next one.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox Turbo.
Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts, as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.